Okay, everybody, we're going to finish physics this year with module 16. You're going to find this module on pages 523 to 546 in your textbook. Let me make sure that this is recording. And let me move this right here. Yeah, it is recording. Okay. So let me get started with the first slide right here. This module is about magnetism, and you're not going to have any math, but there's a lot of conceptual information you're going to have to understand and memorize. Some of the things we're going to be talking about, not all of them, there's a lot of information, are permanent magnets, magnetic fields, how magnets become magnetic, Earth as a magnet, and the magnetic field of the Earth, wires that are carrying electricity and how that creates a magnetic field, how magnets can generate electricity and alternating current. So there's a lot of information, a lot more than this, but no math. There's no extra practice problems either, so that's going to be nice as well. The first thing you need to know is the difference between a permanent magnet versus an electromagnet. Maybe you already know from physical science that few substances are true magnets. The majority of magnets that we use are metals that we have made into magnets. How do we do that? We're going to see in a minute how we do that, but I'm going to tell you now too. We run electricity through the metals, and if it's the right kind of metal, they continue to exhibit magnetism after we stop running electricity through them. Okay, so if the magnet we create continues to exhibit magnetism after we stop running electricity through it, we call that a permanent magnet. But we have magnets that are only magnets when we run electricity through them. Those are called electromagnets. If we stop running the electricity through them, it stops acting as a magnet. Okay, so far so good. If you have questions about the difference between the two of them, ask me on Friday, or you have to read the book as well. I'm going to assign you to read the book, but you can also email me. Okay, permanent magnets, we're going to see them in more detail, are dipole magnets, meaning they have a south and a north pole. Let's look at them in more detail. Hopefully you already know that, but poles that are different poles are attracted to one another. North to south, south to north. Same poles are repelled by one another. So north to north are repel, south to south also repel. Okay. Magnets are magnetic dipoles. Electric dipoles can be made into monopoles, meaning you can have a positive electric pole and a negative electric pole. Just think about batteries. We cannot do the same thing with magnets. Let's look at these in more detail. People have tried, but we have not been able to do monopoles out of magnets. We cannot just have a magnet that has a north pole or a magnet that just has a south pole. Every time that you cut a magnet in half, it develops a north and a south pole. And you can cut it into as many pieces as you want. It keeps developing the north and south pole. So all magnets exist as dipoles. Okay? So far so good. Now, you need to be able to draw magnetic fields, and we draw them using lines, just like we did with electrical fields. Exactly the same. We're going to make lines coming out of the North Pole. So here you have lines coming out, and they need to go into the South Pole. The number needs to match. Look at this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Well, 7. There are 8 here and 8 here. I counted wrong. But anyway, out, in, out, in. This is out, in. So they need to match. Anything that comes out needs to have a place where it comes in somewhere. So when you're drawing these lines, make sure that you make the same number going out as you have coming in. Also, if your magnetic field is strong, because maybe the magnets are very close together, okay, Then you need to draw more lines to show me that you understand that the magnetic field is stronger in that space, okay? And once again, for everything coming out, you need to have a line coming in. You need to show me that you understand that things that repel one another will not have lines going in and out. They're going to be parallel to one another. They're repelled by one another. Lines do not cross ever, just like in electrical fields, the lines do not cross. Magnetic field lines do not cross either. Your rules about how to draw magnetic fields are on page 525. They're also listed right here, but I just went over them as I was explaining to you how this worked. So the same thing is right here in writing if you need to read them. You need to be able to draw magnetic fields. So if they give you a bar magnet or a horseshoe magnet, if they are attracted or they are repelled by one another, you need to be able to show me that, all of it with lines. Let's look at the bar magnet right here, coming out of the north, going into the south, okay? It's magnetic everywhere. So if you made 3 here, you need to make 3 on this side because it's the same, okay? The magnet is the same on both sides. If you have 1, 2, 3, 4, 5 coming out of this pole, you need to have 5 coming into the south pole. This right here is in the U form, strongest in the middle, lots of lines right here, less on the other ends. But for every line that you have coming out of the north, you need to have it coming into the south. These arrows should be pointing the other way. Forget about this right now because we're not going to talk about electromagnetic fields right now. Later, we're going to talk a tiny bit about them. But please make sure that if you have 2 magnets like this, you have lines everywhere. There is the attraction between the 2, but also there is magnetic field lines in the middle and in the ends. So everywhere. And if they are repelled, you need to draw them this way, okay? So how to draw? Study these examples right here because you're going to be drawing it yourself in a second. You also need to be able to calculate how strong or how the distance influences how strong the magnetic field is. If the magnets are pulled together, they're attracted and they're pulled together. If you decrease the distance between the 2 of them, then you also increase the magnetic attraction between the 2 of them. You do that by, you can calculate it mathematically by squaring the distance. So let's look at the examples. If I double the distance between 2 poles, the strength of the attractive force between them will decrease by a factor of 4 because you doubled 2 to the 2 is 4. Let's look at the other example. If I decrease the distance by a factor of 3, the attractive force between the poles would increase by a factor of 9. So remember, 3 to the 2nd power equals 9. So you have a mathematical way to calculate how fields behave by increasing or decreasing the distance between the magnets. Okay. Example 16.1. Draw the magnetic field lines for the situation below. So they're going to give you different situations, different magnets, and you are going to have to draw what's going on there. Let me get my pen. Let me get a pen right here. Let's see if I can get a pen. Remember that lines need to come out of the north and go into the south. So just draw that. From the north to the south, as many going out as going in. Okay? Arrows going that way. Now, for the other half of the magnet, you have to do it the other way because the North Pole is at the bottom right here, going that way. Big arrows everywhere. Now, remember that you still have a magnet on both sides of this drawing. So, going out of the north, going into the south, going into the south from the north, as many going out as coming in. And my point is to show me that you understand how the direction is going. North is up here, so go to the south, north to the south. I did 3 on this side. I need to do 3 on this side, okay? Just remember that the magnets look the same So if you did 3 on this side, you need to do 3 on that side. Are we done? No. This is a pole, this is a pole. These are still poles. So out and out, in and in. I did 2 out, 2 in. Same thing right here. I could have done 3, okay? Because I'm just doing 3. But out of the north, 2 and 3. 3 coming into the south. And probably you can draw this better with your pencil, better than I can do with my cursor right here. But remember to be consistent, okay? Anything that comes out needs to come in, and because they are the same, these two magnets look the same to me. If you make 3 on this side, make 3 on the other side. Let me erase this so we can move on. And you have on your own. If you want to stop now and do on your own, you can do that. This module does not have extra practice problems, so it's up to you. Let me go and try to change my cursor and see if I can move forward. No, I don't want that. Let's see if I can go back and now move it. Yep. Okay. How magnets become magnetic. You are going to learn about this scientist, Hans Christian Ørsted. I don't know how to pronounce his last name. He was Danish. But in 1819, he discovered that electricity produced a magnetic field. And you are going to be recreating his experiment. You're going to be doing the experiment yourself. You're going to learn that electricity has a magnetic field. You already learned about electromagnetic fields before, electromagnetic radiation. Remember how they had both components. So moving charged particles creates a magnetic field. Electricity is just electrons, which is a charged particle moving, creates magnetic fields. The electrons in an atom are the charged particles in motion that cause the magnet to be magnetic. Okay, those two things are facts that you need to know. So all atoms have electrons, all of them. All electrons can move. All electrons have magnetic fields, but not all substances are magnetic. How is that possible? Well, in non-magnetic materials, the magnetic field of each electron cancels each other out. Let's look at these in more detail, okay? So let's see how this happens. If all electrons are moving particles and all moving particles create electrical fields, why not all substances are magnetic? You're going to be doing the experiment, but let's talk about why. Okay, here we have an atomic nucleus, is an atom, okay? The electron right here, okay, has a north and a south pole, is creating a magnetic field. All electrons do that. But we know that even though all electrons of all atoms do that, not all atoms have magnetic fields, and not all substances that have atoms that have magnetic fields are magnetic. So we're going to be looking at 3 different kinds of substances. Let's start with the first substance, what we call diamagnetic substances. In some atoms, the electrons are arranged so that these magnetic fields cancel each other. So these represent electrons in the atom, and these electrons, their configuration is such that the electrical fields of one electron cancel the magnetic field of another electron. So if you see those little arrows pointing in different directions, these are electrons. So the atom itself does not have a magnetic field in diamagnetic substances. Now, sometimes, let me look at another slide that talks about diamagnetic substances. The definition is on page 528. So when you need to learn your definition, you're going to go to page 528 and read these and memorize. What is a diamagnetic substance? It's a substance that is made up of atoms with no net magnetic field. The atom itself does not have a magnetic field because the electron configuration is such that the magnetic fields of the individual electrons cancel each other out. So here you have it. If you put it in the middle of a magnetic field, there is nothing there happening. They don't express any kind of magnetic field. Now, let's go back for a second. Remember that this was about electrons canceling one another. So the atom itself was did not have a magnetic field. Diamagnetic substances. Now, there are two other kinds of substances, paramagnetic and ferromagnetic. In the substances, the electrons have those magnetic fields, and they are arranged in a way that the atoms themselves do have some kind of magnetism. Let's look at them in more detail, each one of the substances in more detail. We're going to start with the paramagnetic. Okay? The definition of a paramagnetic substance is in page 529, and it reads like this. Then we're going to talk about it, but let's read it first. Is a substance whose magnetic atoms, so remember those electrons do have magnetic fields that do not cancel one another, are arranged so that their individual magnetic fields cancel out. So the atoms themselves now are canceling one another. Not the electrons, but the atoms, the magnetic field of the atoms is canceling one another. Okay? Now, under the influence of an external magnetic field, like you can run electricity or maybe you have another magnet around it, these substances produce a magnetic field that is in the same direction of the external magnetic field. So remember, the atoms, their magnetic field cancel one another, so the substance itself does not act as a magnet. But if you have a magnet around them, or you have created an electromagnetic magnet around them, they will align, the atoms' magnetic fields will align so that now the substance will act as a magnet. But as soon as you take the influential magnet out, it will stop acting as a magnet. Okay? Now, let's continue. What about those ferromagnetic substances? Well, in this case, the definition is on page 529. You have a substance whose magnetic atoms, so remember that the electrons are, the magnetic fields of the electrons are not canceling one another. The atoms now are magnetic. But now look at this, the magnetic atoms are aligned so that their magnetic field add to one another. In the previous one, they were canceling one another. Now these atoms, those magnetic fields in the atom, are aligned and they create these regions. You see these regions right here represented by colors. They're called domains. They're called magnetic domains. And the atoms in this yellow area have magnetic fields pointing in the same direction. They're added to one another. The problem, if you notice here, is that the different regions cancel one another. You see that? They're canceling one another. The nice thing about it is that you can make them align. Okay? You can make them align by doing the same thing we did before, by creating or putting another magnet around them. You can wrap another magnet around them or using electromagnets around them. And usually when you do that, these become permanent magnets. So this kind of magnetism stays, usually, okay? So ferromagnetic substances will become permanent magnets. Now, summary. You're going to find your summary on page 530. You have all this information. I'm going to read to you. If you have questions, please ask. Summary. Each of the electrons that orbits the nucleus of any atom produces a magnetic field. Everybody clear about that? All electrons have that. In some atoms, the electrons are arranged so that these magnetic fields cancel. Substances made up these kind of atoms are called diamagnetic substances. So remember these ones right here, their atoms do not have a magnetic field. If, however, the electrons in an atom do not cancel out each other's magnetic field, the atom now is magnetic. A substance made of such atoms can be either paramagnetic or ferromagnetic. If the atoms are completely misaligned so that their magnetic field cancel out each other, then the substance is paramagnetic. I know these words are just so strange, but I hope it's making sense, okay? From the electron to the atom, now how are the atoms arranged, okay? So that's where we are, how they are arranged now. If instead of the atoms align themselves in little clusters called domains that each behave as a tiny magnet, then the substance is ferromagnetic. If these clusters called domains happen to align, then the ferromagnetic substance becomes a magnet. So summary, up to now what we have covered. Now, this is another example, okay? It's exactly the same thing we have talked about, but it's very important for you to understand that. Look at the magnetism here pointing in random directions. No external magnetic influence, nothing. It's not acting as a magnet. They're pointing in different directions. Look at this right here. They're ordered. They're kind of pointing in the same direction. Strong external magnetic field applied. They're pointing in the same direction. It's acting as a magnet. Now, if you remove this magnetic field, might be another magnet or an electromagnet that you apply to it, and it continues pointing more or less in the same direction, you have created a permanent magnet. So you have not the domains continue pointing in the same direction. Domain do not reverse completely. That is a permanent magnet. Okay. There you go. You're going to be playing with these. Experiment 16.2. You're going to be, if you have the materials at home, you're going to be playing with it. Okay, Earth. Earth is the biggest magnet of all. It's just like a big magnet. It's a little bit tricky because of different things, but let's look at this for a minute, okay? Look at that. Look at the arrows coming in here. They're coming out of here. What does that mean? They're coming out of here means this is really the true magnetic north. This right here is the true magnetic south. But this is the North Pole, and this is the South Pole. Okay? The geographic North Pole is really a magnetic South Pole. And your geographic South Pole is really your magnetic North Pole. Not only that, but hopefully you already know that your poles are not exactly on the axis in which Earth spins, okay? So they are a tiny bit to the side, just so you know. It's tilted, okay? They are tilted. Let me read this right here. Earth's magnetic field, also known as the geomagnetic field, is the magnetic field that extends from the Earth's interior to where it meets the solar wind, a stream of charged particles emanating from the sun. So there you go. You already know that the middle of the Earth is full of molten iron. And that molten iron is really spinning. It's moving around and around. That creates a magnetic field. Okay, and these lines right here that you might need to be able to draw. I'm not going to say anything about it, but you might be able to draw this on your own. You should probably be able to do that. Will come out and go as far as where the solar wind stops them. Okay, so if the solar wind reach up to here, that's how far the magnetic field goes to. But remember, geographic south is magnetic north. So lines coming out of here and coming in at the top. That's all you need to know about that. Okay. Now, I think I have already mentioned this, but here it is. When a current flows through a conductor, so where we know how we are able to carry electricity through conductors, a material that carries electricity is a conductor. Different metals conduct electricity better than others, but if we can do that, if we can conduct electricity, then we can also generate a magnetic field. And the magnetic field that it generates is circular. So here we have a conductor, it's a metal. Right now we don't have current running. I represents your current, so it's 0. The magnetic field right now is pointing at 0 really. But as soon as you are running electricity, here you go, the current pointing that way, then you have your magnetic field going around and around in a circle around the wire. Okay? You're going to have to be able to draw that. Let's look at this. There's a rule about how to draw that. It's called the right hand rule. So you're going to use your right hand. You are going to be holding the wire with your right hand. You're going to point your thumb up in the same direction as the electrical current. If the current was pointing the other way, then your thumb would have to point down. But right here, the current is pointing up. So your thumb always points in the same direction as the current. The way your fingers wrap around the wire is the direction your magnetic field is turning. So look at your fingers. The fingers are going this way. The magnetic field has arrows going that way as well. You need to be able to do that. If you cannot visualize these in drawing, get yourself a piece of a pole or something that's like a pencil, okay? Under your eye and put your thumb up and see how your fingers curl, because you need to be able to draw these. What do I mean? Look at this. Example 16.2, page 530.